Okay, I just want to give a very, very brief overview of the required practicals that you've done whilst you've been doing the A-level course, all right? So the first one was waves on a string, so here you find the fundamental frequency. What you were doing was you were adjusting. In this one here, you've got the fundamental frequency, a wave on a bridge. Here you've got a signal generator which is vibrating. This vibration generator, sorry. And what's happening is you're using the equation F equals 1 over 2L times the square root of T over mu. This here is mass per unit length. This here is tension given by this, so 100 gram mass in this case would have been 1 Newton. Length is the length between these two, between the movable bridge and the generator, and F is the frequency where we get this pattern here, where the distance between the nodes is like half a wavelength. Okay. Now, when you've done this experiment in school, you will have changed L and then changed the signal generator to find F. So you would have been able to find the relationship between F and 1 over L. You'd be able to draw that graph. Now, with all of these experiments where a graph is drawn, this one's a very straightforward one, because if we think about the graph of this, if we did F against 1 over L, which is really straightforward, we would have got a straight line through the origin, and if you think about y equaling mx plus c, then we can see that the y-axis is f, so f equals m is obviously the gradient times by x. Now x in this case is 1 over L plus c. Now c, the y-intercept is 0, so that's irrelevant. So, excuse me, my daughter's just come in to ask me something. Hang on. What's up?
Where's the tablet?
There. It's okay, my love. Okay, sorry, I thought I'd paused it. Right, so this here, so if we've got f against 1 over L, then, so that there's our x-axis, so our gradient in this case would be everything else from this equation. So if we look at this equation here, we've got a half here and square root of t over mu. So the gradient in this case, the m, is equal to 1 over 2 times the square root of t over mu. Okay? Now, you're going to get a question which is going to require you, and it won't be familiar, you're going to get a question in the exam which requires you to look at a graph that you're not familiar with. You're going to look at an equation, and you're going to have to determine what the gradients and the y-intercept are in order to calculate different values. Now, obviously, this is a very straightforward example of that. There are other things we could have done. We could, for example, have said, well, f squared equals 1 over 4 L squared t over mu. Now, often when you see equations like this, where you've got a square root sign, the first thing you would normally do is that. Now, with something like this, you could then do a graph of, so this is other options you could do. So, for example, you could do a graph of f squared against 1 over mu. Now, if you did that, your gradient would be t over 4L squared, because that too would give you a straight line through the origin. So there are lots of ways of doing these experiments to determine different values, but it's really important, really, really important that you're clear. Whatever you're measuring and wherever you're changing, everything else is kept exactly the same. You use those values and you repeat in order to determine some variables which, if you can plot them on a graph, the gradient and the y-intercept will give you the values that you're looking for. Okay, the next one is Young's slits and diffraction gratings. So this one here, you've got double slits. So this equation, I should say, we've got W is lambda d over S for this one. W is lambda d over S, and this experiment here is used to determine the wavelength of light. Now, hopefully you all remember what causes this interference pattern on the other side. So W, this is our fringe spacing at the other side. D is the distance to the screen. S is our slit separation here, because this is obviously young slits. So we've got monochromatic coherent light coming through, and we've got this interference pattern where we've got constructive interference and so on. So in order to make this experiment work, we need to look at how we can make it more accurate. Now, it's quite important when we're doing this experiment that one of the things we could do is by increasing D, we are going to make this fringe pattern more spread out, and therefore it's going to be easier to measure. Now, when we do measure it, another thing that's important is if we're measuring the distance between two lines there. Now, when we do that, what we would notice is that it's very difficult to measure. Even if D is large, it's still difficult to measure. And there's an inherent uncertainty in the first value and the second value. So to minimize that, it would be better if we measured from, say, 10. If we measured 10 of them, so counted 10, and then we've got an uncertainty here and uncertainty there. So we measure this, divide by 10, but our uncertainty is also divided by 10, so it means that we're reducing our uncertainty all the time. So that's a good way to make this experiment, excuse me, to make this experiment more accurate. Now, a big thing about this is going to be the safety in using lasers. So obviously they're very dangerous. Strict precautions need to be observed all the time. Never look into the beam or let anyone else look into the beam. Don't point the beam at anyone. Avoid reflections of the beam. Keep your back to the laser when it's on. Always switch off the laser when it's not in use. Always work in a well-lit room so your eyes, so there's no risk of your eyes dilating and so on. And also, really, if it's going to be anywhere near the door, you have to put a sign on the door to make sure that it's safe. If people are entering, that they're not going to be walking into the laser beam. Okay. So we could, you wouldn't, but you could. We'd normally do this experiment, and you could, if you wanted to, you could change D, measure W. You could plot a graph of this if you wanted to do it like that. But normally you wouldn't do that. Normally you might try it for different slit separations for a given wavelength of light. In school, what we did was we used a particular laser. So you may have had a green laser, a red laser. And what you will have done is you will have done Young slits experiment, and you will have done it. You may have done it for say 2 values of D or 3 values of D. And you'd have looked at W, and you'd have taken an average and worked out the wavelength of light for this experiment. But then what you will have done is you will have done the next experiment, which is n lambda is d sine theta, with the same laser. And then you will have done the experiment again to see if you got the same value for lambda. Now again, it's the same idea. Now this here is your order number. So we get our central maximum here, and then we've got n is 1, n is 2, and so on. And n lambda is d sine theta. And now this here, obviously this is our grating spacing, so it might say things like 300 lines per millimeter. So we have to make sure that we understand that means in 1 millimeter. There are 300 lines, and therefore we know what the distance between them is. Now this here, these obviously are not equally spaced. So it's important then, for this particular experiment, what you would do is you would obviously make this as large as you possibly can again, and just in the same way. You can't count across and divide for this experiment because they're different distances apart. But what we can do is we could say, well, what's the first order number? So make n as 1, so find this one here, and the distance between there, and then we'd find this angle here. Now, that there would enable us then to determine the wavelength of light. Now, it's important. We wouldn't use a protractor for this. We'd use trigonometry. By making D as large as possible, we can make this as large as possible, and we could calculate the angle. If we use a protractor, there's going to be large errors in that. So this would be a more effective way because our big reading enables us to be far more accurate in our results, okay? Now, you would then repeat the experiment for n is 2. So you'd look at your second order, find out what theta 2 was, and you'd be able to determine the wavelength of light again. Now, once you've done this, you can then take an average of the wavelengths of light in order to determine what the wavelength of light was. All right, so that's basically, obviously this is very brief, but that's something we could do. But yeah, it's one thing I would suggest though is that we remember that when we this theta, don't use a protractor, use tan theta is x over d, where this is x. Okay, so the next experiment we did is g by freefall. Okay, so now it's important that we understand this. So our theory behind this was that we were just investigating. We know that a free-falling object is falling vertically under gravity. There's no other forces acting on it. Obviously, in reality, there always are other forces acting, but they are irrelevant at such speed. So what we did was we were using S equals ut plus a half at squared. And because the object was released from rest, u and doesn't matter, so we've got S is equal to a half at squared. So from that then, this is obviously h, so h, which is the height, is a half, and the acceleration is g, so it's a half gt squared. From that then, we could plot a graph of t squared against h. So if we did a graph there of t squared against h, t squared against h, here you've got, if I just write it over here, so you've got t squared equals 2h over g. So if we did a graph and said, well, y equals mx plus c, we can see that our y-axis is obviously t squared, our x-axis is h. So here we could see then that two over g c equal to 0 anyway, and we could see then that the gradient would give us 2 over g. So from that we could calculate the gradient, because your graph would be a graph of t squared against h. Okay, now for this one here, there are lots and lots of ways to do it. You can use light gates with a computer, you can use photography, video frame analysis, you can do all sorts of things. What we did was we used this exact experiment, and what happens is there's electric current passing through here. As soon as this is switched off, the ball obviously falls, but as soon as this is switched off, the timer starts, the electronic timer, and as soon as it passed through, what I did here was, rather than using light gates, when the ball passed through some foil here, it broke the circuit, and the timer automatically switched off, and it gave incredibly accurate values. And what we did was we changed h and we found t. Okay, and we plotted a graph of t squared against h, and from that we were able to find out a value for g. It was a very straightforward experiment. With this, to make sure it worked, the timer had to be reads about 100th of a second. The obviously clock stopped when it hit the trapdoor at the bottom, or the foil at the bottom. We needed to do each reading. Now this was important when we did our table. We did each reading 3 times for each height. Okay, so that gave us just because of our errors that we'd have, our random errors. We did it 3 times, repeated 3 times for each height. And safety-wise, we had to be careful, obviously, with the wires, that we didn't have any short circuits, and that we had to have a container underneath the trapdoor, which caught the ball, which stopped it falling on the floor, which would have been a trip hazard. Okay, so that's how we did that one. And it was very, very straightforward, 2 over g being the gradient. Okay. If, by the way, we did have, on this graph here, if it didn't go, this is something I talked about in an earlier video actually, if it didn't go through the origin, if it went here or here, that would suggest a systematic error. So that would say there was something wrong with our setup, and there's something which would make all of our results just slightly out. Okay, by the same amount each time. So if it doesn't go through the origin, that suggests a systematic error. The next one we did was Young's modulus. Okay, so Young's modulus, very, very, very common experiment. Obviously, Young's modulus equals stress over strain. And which equals force over area over extension over original length, which equals FL over A delta L. Okay, or E is flea in the olden days. Right. So this experiment here can be done horizontally or vertically. The extension of the copper wire is very, very small. It's only measured in millimeters. So this is a very difficult experiment to do. So we use a vernier scale. Sometimes you can use a micrometer instead of a vernier scale, but you do use a micrometer, obviously, to measure the diameter of the wire. And so it's important that you watch the video on that so you're clear on how to do it and how to use the vernier scale. So we used thin copper wire, and one of the things that was really important was to have a crash pad under the weights to prevent them hitting the floor directly when the wire breaks. We do not put our feet under the weights, and we wear goggles all the time, because if the wire breaks, the wire could obviously contract and then flick back and go into your face or into your eyes. So you have to be very careful with this experiment. Now, if you don't do this horizontally, you do it vertically, it's all the same. So at the top, you've got a beam attached to a ceiling structure. Now, this is a rigid beam. This means that if we get something called ceiling sag, so if the ceiling bends slightly because of the weight of the mass, the control wire or the comparison wire will move exactly the same amount as the test wire. So it doesn't matter. Having a comparison wire also means that any temperature fluctuations in the room which cause the wires to expand will be negated. So it won't matter, because it's really important to having this test wire here, because anything which happens to that also happens to the test wire. So from that, then, all things can be judged to be equal. So we then can see, we measure the diameter of our wire using a micrometer in several places. We take an average, and so we are happy that we can calculate the cross-section area of the copper wire accurately. And then we use this vernier scale. We add weights to it. As we're adding weights to it, so we're changing the force on it, and we can measure the extension of the wire. We're able to plot a graph, stress over strain, and calculate the Young's modulus of the wire. Okay, because we're measuring, we know the original length, which we measure using a ruler. We use our vernier scale to measure the extension. We use a micrometer to calculate the diameter and hence cross-section area, and the force, or the change in force, is done using the different masses here. From that, we can calculate the Young's modulus of the wire. Okay. Now, normally what we do here is you do a graph of, say, you could do a graph of force. You could do a graph of, say, force against change in length, and that would give you a line which go up. It actually would curve at the top, but you get a nice straight line here. And you can see then, you'd be able to work out from that, you could have, so if E equals FL over A delta L, if we make that equal now to Y equals mx plus c, so now we've got F equals, now our x-axis is good because it's just 1 over delta L. So in this case, if it's 1 over delta L, we can see then that the gradient here, the m, the gradient, if we look at what are we multiplying by, so here, it's not over 1 over delta L, my apologies, it's not 1 over delta L. Being silly there. My apologies. I'm just going to rearrange the equation there because it's. I've just got to rearrange it so it makes sense. Because we're doing a graph of F against delta L. So F equals E A delta L over L. So here, if we do the form of y equals mx plus c, we've got y as F equals, the x-axis was delta L, not 1 over delta L, my apologies, it's just delta L plus c. So what would our gradient be here? So we can see then our gradient, so we've got delta L, so F is proportional to delta L, but EA over L would be our gradient. So it's M, the gradient is E A over L. Now, this is quite simple to do because we've worked out the cross-section area with our micrometer. L was the original length anyway, so from that the gradient can be used to determine the Young's modulus for the given wire. Okay. Now the next experiment we did is the determination of resistivity. So we've got some constant and wire here, and it's, I suppose the equation you would use, R is rho L over A. So for something like this, what we'd normally do is do a graph of resistance against length. So here we would have resistance against length, and for this experiment here, you've got again y equals mx plus c. So we've got R equals, the x-axis is obviously L plus C, so it's rho over A. Okay, so the gradient in this case is rho over A. So that there will give you a gradient of rho over A. Okay. So rho would be the gradient times A. Now, this might not necessarily go through the origin. It should, obviously, when we look at the equation, it should go through the origin, but it might not go quite through the origin because, obviously, of resistance in the wires. So you might have some sort of systematic error, but that's caused normally by just tiny amount of resistance in the normal wires. Okay. So for this particular thing, all you're doing is you're measuring the resistance using voltage divided by current, R is V over I. And you're changing the length, so you're moving this. Now you're using a crocodile clip, and the crocodile clip ensures that you get a really, really straight, very narrow connection, so that it's unambiguous. So you can get a really accurate reading for L. Now the resistance of the wire like this is only a few ohms. Now an ohm meter isn't suitable for measuring the resistance with any degree of accuracy for that. So we have to use an ammeter and voltmeter, and we use V over I to get a really accurate reading for the voltage. We set up the circuit just like it's shown here, and we just make sure we're very, very, very careful with our crocodile clip. Now, we use those low voltages, but it's really important to remember that when we did this experiment, we were careful to prevent obviously any short circuits, but also we do each reading as quickly as possible because we don't want the wire to heat up. And obviously we're using very low currents anyway, but we don't want the wire to, because there's such low resistance, there's a high current. So we just have to be mindful that this high current can change the temperature of the wire and therefore change the resistance anyway. So when we take each reading quickly. We repeat each reading several times, take an average, and do it for different lengths. The other thing that's worth mentioning is obviously this A here. We take the diameter of the wire and we use obviously the cross-sectional area equals pi d squared over 4, or pi r squared if you want to just half the diameter from the micrometer. Okay, so that's something that we would do to work out the resistivity of a wire. Okay. The next one was EMF and internal resistance. This one here, the equation you would have used here is that V equals the EMF minus IR. Now, this equation here, this is a really complex experiment. For some people, don't like this at all. There are lots of ways to write down the EMF equation, but we're going to use it in this format, and then I'm going to rearrange it again to say that V equals minus RI plus E. Okay, so we've got voltage equals minus RI plus EMF here. Now, the reason we do this is because when we're working the EMF of the battery out, we're looking at this terminal potential difference, the potential difference of this voltmeter. As we change this resistance, obviously we're going to get different values for current, and that enables us to work out the internal resistance of the battery. Okay, so when we do this and we look at the equation y equals mx plus c, that's why I've rewritten the equation like that, because the y-axis here is V, this voltmeter here. The x-axis is the current, which is here, and c is the intercept there. So this intercept tells you the EMF of the battery, and the gradient is minus R. So the gradient here was minus R, and that enabled you to work out the internal resistance of the battery, because it is minus R, and the y-intercept was the EMF of the battery. Now, with this, we do this, we've just got to make sure when we do it, I'm thinking there's nothing really, really dangerous in this one. Obviously, low voltages, we've got to take care with the wires to prevent any short circuits. Be careful not to just be. There's not much to say on this one. It's really easy. Just be careful, okay? And the next one here. I'm trying to think of dangers. Can't think of any dangers with this. I'm sure there are some. Right. That was the grade. That's what you do here, and it's obviously EMF and minus R is the gradient. That's the graph. So the next one we did. Oh, we are. But we got some dangers here. We got a danger somewhere with the mass. These experiments are so safe, right? So this one here, T is 2 pi times root L over G. So this is another experiment you did, and obviously you were trying to work out a value, I'm guessing, for G from this. So when we did this, we could plot different graphs to find this out. Now, this is quite important, actually. When we're taking readings for time for a pendulum, it's important that we take, say, 20. Now, we know that each oscillation is the same amount of time, but human error, I realise stop clocks measure to 100th of a second, but a human can only do about 1/10 of a second. So there's an inherent error here which we can do nothing about. So to minimise the impact of that error, what we would do is we would time for multiple oscillations. So the error, that inherent error, which we can do nothing about, the human error, which might be 0.1 seconds, whatever, if we time this for 20 oscillations, that error becomes less significant, because when we divide the total time by 10 or 20, however many oscillations we do, we're therefore reducing the uncertainty by the same amount. Okay, so it gives us a more accurate value for T. In this case here, obviously length would be measured with a ruler, but very, very carefully. And we could do a graph to work out G. So what we would do is we would do a graph to work out G. So if we just have a look at this, you would take your readings and you'd repeat obviously lots and lots of times for different values of L. And we would normally, with an equation like this, you would say T squared is 4 pi squared times L over G. Now, if we want to find G, it would probably just say, okay, let's do a graph of T squared against L, and then we could say, okay, so Y equals mx plus c. So the y-axis here is T squared, So that's fine. And that equals m, now x. Now our x is L, let's put our L there, plus c, so that which is going to be 0. So therefore we can see then that the gradient of this graph, the gradient is going to be 4 pi squared over g. So the gradient of this is 4 pi squared over g, and from that you can determine g. So g is 4 pi squared over the gradient. And that's how you do that experiment. And it's exactly the same theory when we do the mass on a spring. Now it's important to remember with this, how are you going to make it more accurate? Well, you use a fiducial marker, and what that does is it's just a pin, and that obviously you're avoiding parallax error or this sort of thing, and that enables you to get an accurate reading of the time period, because this one of course is the same. It's just t equals 2 pi times the square root of m over k. So this here, you'll be changing just like the other one, L over G. You're going to change m, measure t, and you're going to find out the gradients of your graph. So if I just show you here, so if t equals 2 pi times the square root of m over k, then it's going to be t squared is 4 pi squared m over k. You would do a graph of t squared against m, and the gradient then would be, just like before, 4 pi squared over k. Hopefully that makes sense. There's nothing to this one. Just please make sure you're avoiding parallax error, and you're mindful of this, the fiducial markers and so on, because these are just small little things which you can be asked about. This one's actually got a hazard I can mention. This one, the hazard obviously is that the masses could fall off. That's the main thing. So you got to make sure that you keep your feet clear and everything else. Don't stretch it beyond its elastic limit and so on. Okay, I'm just going to pause this and see if I can ask my daughter to lower music. Right, sorry about that. She's just been in to show me. Anyway, mad. Right. What are we on now? Required practical 8 will be next. So that would be required practical 8. Boyle's and Charles' law. All right. So this one here. Which one should we do first? That's Charles' law there. Oh, I don't like that experiment with Charles' law. And Boyle's law. Now the Boyle's law experiments, the way we were asked to do it was this way. Now the results were awful for this particular experiment, so I changed it slightly for my students. Okay, so there are lots of ways to do this, but I didn't favour that. I'll just check the AQA website because I'm just going to have a look how AQA say. I think they're doing it this way, which I don't like. I'll just check. Okay, I've just got a picture. This is I use the equipment on the right. I wouldn't use. I did have used the equipment on the left at school, but I wasn't happy with the results. I thought there were far too many uncertainties in it. So I've gone for the equipment on the right. So I've used this. Now with Boyle's law, what you're saying is, for Boyle's law, you're just saying that P is proportional to 1 over V, or that PV equals a constant. And all we're doing here is we're trying to confirm Boyle's law. Okay, so with this, you've got PV as a constant, and so all you're trying to do, so in my case, I use the pump here, I've got some oil here, and I'm changing the pressure and looking at the impact on the volume here. Now, the same things in this experiment here, which I have tried. This is where we're changing the force here. We know the cross-sectional area here. And what we're doing is, from that, because we know the cross-section area, we know the force on it, we can work out the pressure. We can see the volume as it changes. So this is a way to do Boyle's law. It's not a way I like at all, to be honest. And I have tried it several times now. So instead, I purchased this apparatus here, which enabled us to see it. So all you're seeing is this. You do a graph of pressure against 1 over volume, and a straight line through the origin will confirm Boyle's law. And that's how we did it. This one here, I really disliked. Obviously, you've got to be careful. You're measuring everything, so you've got to measure everything. So we used, because we have done this in school, the results were appalling. But the diameter of this with a micrometer, we've got to make sure, we've got to be careful for safety to make sure the thing doesn't topple, so we have a counterweight and so on. But it really isn't a good experiment at all. This traditional way of measuring Boyle's law is far better. And with this here, the pressure's relatively high, not particularly high, but we just got to make sure our connections are all very well sealed. And it's checked by a technician or teacher before any students go near it, just to make sure there's no leaks and so on. Now, Charles' law, again, I don't like the way the AQA have done this. I don't like the method they've used. We do have the sulfuric acid method, and we have trialled this in school. However, again, the results aren't very good. So I purchased some what are called gas syringes and put the gas syringes in a water bath. So hopefully you remember, we put a gas syringe into a water bath or into a Bunsen burner with a thermometer and changed the temperature. And we measured how the volume of the gas changed with temperature, because Charles' law is different. So Charles' law states that volume is proportional to temperature, okay, or that volume divided by temperature equals a constant. Okay, so we did it the much more straightforward way than using the sulfuric acid, just using a gas syringe in water, change temperature of the water, and the gas syringe is really good because it's like the ones they use in A-level chemistry, where it slides very easily and enables you to see the volume change as you change the temperature. Now on that, you would then be able to draw a graph. So you, just on Charles' law, it's just a quick thing here. It's important to realise that when you do this, you would draw a graph and you would have volume obviously on here, and you would have the temperature here. Now, if your temperature was in degrees C, now if your temperature was in degrees C, then what would happen is you would get a straight line which would go through there, like that. Okay, now obviously we take readings at different points. You'd cool it down as much as you could, and you'd take all your readings, and you'd hopefully find that they fall on a line of best fit like this, because volume is proportional to temperature. But we can extrapolate that, and when we extrapolate it, we hopefully find that it reaches the origin here, and obviously that's minus 273 degrees C roughly, which obviously is absolute zero. And so Charles' law enables us to work out a value for absolute zero, and the gas syringe way is definitely the best, I would say, for that. No one ever finds an actual value for absolute zero. There's lots of things. So, for example, it could be things like the air in the syringe did not have time to come to thermal equilibrium with the water bath, and so the temperature of the trapped air is different from that of the water, or the temperature recorded. There's friction. Now, this is a biggie. There's friction between the plunger and the walls of the syringe. This makes it harder for the air to expand. This is particularly bad in the case of the way AQA do it. There could be a leak in the stopper. There could be, the graph also requires a lot of extrapolation. When you do this in reality, the number of readings you're taking in reality, they really is small when you look at the range of the graph. You're taking readings over a range here. And what you're doing then is you're extrapolating enormously down there. So your range of readings isn't actually very big. And then you're expecting to extrapolate all the way down there, which means that there's a massive amount of error, because, of course, any small error here in your gradient, because it's extrapolated to such an extreme, you'd find quite a large error in your value for absolute zero.